time, we started this important discussion of understanding electromagnetic radiation, and we have some prescribed sources that are moving in space and radiating electromagnetic waves. And to do that, we began by looking at the wave equation for a scalar wave that is being driven by some source term. And to solve that equation, the particular solution is found in a general form by convolving the source in space and time with the Green's function associated with the wave equation. So we looked for solutions of this equation, which we found, and we found two kinds of solutions, so-called retarded solutions and advanced solutions, which correspond to either spherical wavefronts that are emanating from X prime or converging onto X prime. Okay? The wavefronts that are emanating from the point are the retarded time solutions. The ones that go backwards in time and converge on the point are the advanced time solutions. Both are solutions. And they're used in different contexts. In particular, in scattering theory, when we think about in and out waves with asymptotic boundary conditions, we often use, in the time-dependent formulation of scattering theory, one uses both the advanced and retarded time solution. But in the current context, where we're talking about a source that is radiating, we're looking for the radiation that emanates from that, then we think about the causal solutions, and those are the retarded time solutions. Those are the causal solutions.
So any particular reason for the naming scheme?
Retardation, I think that's, that is one semantic notion of if something is retarded in time, it's backwards in time. It's one semantic meaning of the word.
Advanced is more
It
complicated.
means it's in my future. That's where that comes from. There's no political context in this. All right. So we then see that if we convolve the Green's function with the source, then the general solution is a weighting of the strength of the source by an amount that falls off like 1 over the distance. But what we see, the wave amplitude we see at our time t, at our position x, depends upon what the source was doing at the retarded time. The retarded time is the time, the current time, minus the time it takes for a light signal to travel from x prime to x. So what I see currently is what the source was doing in the past. Of course, astronomers know this very well. So we can depict that on a space-time diagram where this axis is representing one coordinate of space, and this is time. And thinking about this is my position at the present, time t, and the signal that I see at my position at the present depends upon what the source was doing on my backward light cone. Meaning to say, these are all the space-time points in the past, in my past, correspond to this current time, that correspond to a light signal that can reach that point. And so the total signal that I will see will be a weighting of the sources over all the world lines that cross my backward light cone, added up appropriately with the 1 over distance scaling that's related to the spherical wave. All right? It's a nice picture. So now we're looking at this in the particular context of electromagnetism. This is a general formulation of waves, whether this was the speed of light or the speed of sound. The same mathematics holds, and the same physical description would then hold in that case as well. Things get a little bit more complicated for electromagnetic waves because they're vector waves. Okay? And so anyway, to do this, so we're looking now for general solutions to Maxwell's equations. And to do that, what we do is we formulate things in terms of the potentials. We solve for the potentials given a certain source, and then find the fields from the potentials. So these are the equations, Maxwell's equations without the sources. They are the ones that determine the relationships between the fields and the potentials. And these equations we see have gauge invariance. That is to say, we make these transformations on the scalar and vector potential, then the fields are left unchanged. So there is a freedom we have in choosing these functions that give the same physics. And we can in principle make a gauge transformation in this way. So when we take these potentials and we plug them into the source equations, the Ampere's law and the Gauss's law, then we find these equations of motion for the potentials. Okay? And they can be written different ways depending on our choice of gauge. So two standard choices that are made in thinking about electrodynamics are the so-called Lorentz gauge. So-called because this gauge condition is the same in all inertial reference frames. We get a very simple form for the equations of motion for the potentials, the scalar and vector potentials. And they are just wave equations with sources. Okay? I failed to emphasize here to remind you that in the context of dynamics, the vector potential plays a much more prominent role. The electric field depends not just on the gradient of phi, but also the time derivative of A. And in fact, in radiation, this is the whole story. The rest of it is just there to make sure the field is transverse, in a sense. So for the Lorentz gauge, the equations are exactly of the form we described here, and we have the solution. Okay, and we're going to use this, guys, but I do want to mention that there is another choice of gauge that we can, that is often made, and that's the so-called Coulomb gauge, which is to set, or sometimes known as the transverse gauge. It's called transverse because the vector potential is set to be a transverse field. Its divergence is set to 0. That's a perfectly good gauge choice. If we do that, then phi looks like Coulomb's law. This is the Poisson equation, which is the electrostatic Coulomb's law. That's why it's called the Coulomb gauge. But it's not to say that it's really static, because of course the true electric field depends not just on the gradient of phi, but also on the derivative with respect to A. In this gauge, the vector potential has a wave equation, but with a source term that is only the part. Remember, in our very first problem set, we said that any vector field can be broken up into a part that has that is defined by its curl and its divergence. right? So we can, the part of the source that contributes to the vector potential in the transverse gauge is the transverse part of the current. Okay, and then we can solve this for the vector potential. This is actually a useful form when dealing, as we'll kind of touch base with this a little bit later on, when we're talking about electromagnetic radiation for non-relativistic charges. Because it kind of breaks up the potential into the part that's kind of the static part and the part that's the radiation part. All right, so that's where we were. Anybody have any questions? All right, so what we want to talk about today is multipole radiation. So when we were talking about statics, you know, we had similar kinds of solutions, but instead of the retarded time, this was the local time. Well, actually, there was no time at all. It was static. What we did is we looked at, for example, the situation where we had localized sources and we did a multipole expansion. We want to do the same thing now for the dynamic case. All right? So we're going to look at a situation where we have some localized distribution of sources and they're, you know, doing whatever the heck they're doing. So this is my source. Rho as a function of position and time, and J is a function of position and time. Okay? And here I am, the observer, my beautiful eyeball. And I want to know something about the electromagnetic field at my point. So there's some origin somewhere, right? And the position of the observer we call X. Okay? And so we know now how to find the potentials. We just have to integrate these things. Okay? So we have there's some position of the source, just like we did when we talked about statics. X prime is some position within the source. And there's some script dr, which is the distance from the source point to me. Me. All right? So, well, we just have to do this integral. Now, we want to do this in certain approximations associated with the multipole expansion. So, we're assuming that there is some characteristic size of the source. Some dimension D. And what we talked about in when we were talking about statics is the multipole. One important notion of the multipole expansion is that we were far away compared to the size of the source. We just had net charge, we'd see a monopole. If there was no net charge, then the first non-vanishing thing was a dipole, etc. So the first approximation we're going to make is the assumption there are small parameters. One is that the size of the source is much smaller than the distance I am away from the source. So we're calling R the magnitude of the vector that describes my position relative to the origin. So this seems to be small compared to 1. That was what we had when we talked about statics. But there's another very important approximation now in the context of dynamics. So the sources here are moving around, and we are going to make another, so we have so the first approximation here was that we had a compact source and we are far away. The other approximation we're going to make is that the motion is slow. What do I mean by slow? Whenever we talk about notions of big and small in physics, it's always the ratio of things, okay? Well, we have one important constant here, and that's the speed of light. So what I mean by this is non-relativistic. So we're having the charges are not moving close to the speed of light. When they are, the approximations we're going to make go to hell. And if we had more time, we would study, and one should study, the radiation of relativistically moving charges. Some very important problems, especially in astrophysical context and so forth. But we're just not going to get there, I don't think, this semester. So, what does that mean? That's saying there's some characteristic, not only size of the source, but let's say there's a characteristic time that charges move over distance d. Okay? So that means their characteristic speed is d over t. So what we're assuming here is that d over t is much, much smaller than the speed of light. So those are the two approximations which we're going to make. Now this approximation, yes sir?
So I'm sorry, are you saying that t is like the period of the spin of the object?
Okay, so right now I'm just saying there's some characteristic speed of the charges, and they're moving around. And there's some time scale that it moves from one side of the source. They're moving around in some arbitrary way at this point.
Basically,
and they're just saying that the time that light propagates across the sample is tiny, absolutely tiny, compared to the time it takes them, the charge to move from one place to another across the sample. For example, if I have an atom, okay, we have, an angstrom. The time it takes light to travel across an atom is tiny, even for, well, it sort of depends on how strong the binding is. I mean, for very highly, for very high Z atoms, when you start getting into relativistic orbits, maybe it's not true. But for hydrogen, even though it's moving, 1 over 137 of the speed of light, it's still, the time it takes light to cross a Boreas is tiny compared to that speed. So when we talk about atomic absorption and emission of electromagnetic radiation by atoms, we always make a multipole expansion. Talk about dipole radiation. Okay, so I just wanted to emphasize another point related to this approximation, which is, let's suppose that we look at a particular case where we have harmonic motion. Right, so that 1 over t is like the frequency of the oscillations. So we have maybe an oscillating charge going back and forth. What do we have here? That means that this approximation is equivalent to saying d is much, much less than c over omega, which is like the wavelength associated with electromagnetic radiation that was oscillating at that frequency. So another way of stating for the case where we have harmonic oscillation, and is often talked about as the dipole approximation when you hear about that in, say, perturbation theory in hydrogen atom or something like that, is that the wavelength is much, much bigger than the size of the sound. That's equivalent. It's the same thing as saying that the time it takes the charges to move across a sample is very, very slow compared to the speed of light. All right, so those are the approximations we're going to make, which are useful in a multitude of contexts. And now we want to use that to do a multipole expansion of our potential. So we're going to look at the Lorentz gauge solutions. So let's, for the moment, use the Lorentz gauge. And, well, first of all, one of our first approximation basically is saying that this distance is approximately equal to r minus r hat dot x prime, right? If we just were to expand, remember this is equal to the square root of r squared plus r prime squared plus 2x dot x prime. And if all of the r's are very big compared to all the r primes, you can take this out and expand this to first order action. Should just be a minus, and we get that. That's just saying that this distance is approximately this distance plus or minus, minus the amount by which this is projected onto here, right? Think about this like you did when you think about double slit experiments and the two rays and how you subtract off the little extra piece. Okay, so that meant that 1 over x minus x prime was approximately 1 over r plus r prime over r squared dot x prime. That's the kind of expansion we used when we were doing the multipole expansions. This has nothing to do with the Lorentz gauge. We'll come back to that. So I don't want to confuse you. This is just this. Okay. So that's one approximation. You can expand this, of course, to higher orders. We'll get 1 over r cubed, et cetera, et cetera. That appears here. But there's also this fact that the retarded time here, remember the retarded time is the local time at my position of observation minus the time it takes light to go from the source point to me. Now, there's many retarded times. There's a retarded time from the origin. There's a retarded time from this point. There's a retarded time. They're all slightly different. But they're not very different because this source is very compact and the thing is moving very slowly. Okay? So, let's do a little aside over here. Let's consider a function of t evaluated at the retarded time, which is f t minus for some particular point of observation and some particular point within the source. Now, under the assumption that the time it takes light to travel across a sample is tiny compared to the motion of the particle, we can do an expansion around the retarded time at the origin. The additional retarded times from other points outside the origin is a small correction. So, we write this as f at t minus, we have over here, r plus r hat dot x prime over c. So this is the retarded time from the origin. And this is the little extra piece of the retarded time that's coming from the fact that I'm at some source point that's not exactly at the origin. Okay? So this, I'll just call T0. That's the retarded time.
In the first arrow, so I have a C denominator.
It should indeed, thank you. Sometimes C is 1 in my head and sometimes it's not. From R. Okay, so under the slowly varying approximation that this is small, compared to T0, then we can do a Taylor series expansion of this, evaluated at T0, plus the little extra piece of the retarded time times the derivative of this evaluated at T0. Dot, dot. Approximately. Okay. All right, so I'll call this F dot at T0. All right, so now we have the ingredients. Let's look at our potentials. Now let's use Lorentz gauge. The scalar potential, which is has the exact expression as such, is approximately equal to that plus the source evaluated at x prime at the retarded time from the origin plus r hat dotted into x prime over c, the time derivative of the charge density evaluated at that time. So let's see what we got here. Well, this, together with these guys, gives us what we had in statics. So what do we have here? So this is equal to 1 over r the total charge, which doesn't change, plus r hat dot p, the dipole moment evaluated at time t naught over r squared. Let's see, plus r hat over c dotted into the time derivative of the dipole moment, plus over r plus dot dot dot. So, what do we see from this so far? Well, so Q here is the total charge. This, of course, the total charge is conserved, so that's independent of T. T is the dipole moment at the retarded time, which is the integral, you'll remember, because I know you remember, of weighting the charge density by its position. But of course now that can vary in time. So this is the monopole. and this is the electric dipole. So good. So these terms are familiar, maybe. This is what we had from statics. This is what I would call quasi-statics up to dipole. So this was our monopole potential. Remember, it fell off like 1 over r. This was our electric dipole potential falling off like 1 over r squared with that particular first order or harmonic shape. But now we have a new thing that we didn't have in statics because we didn't have things changing in time. As we'll see, this term gives rise to 2 effects. There's another quasi-static induction. So you remember, if we have currents, we can have that change in time. We can have changing magnetic fields, and those changing magnetic fields, through Faraday's law, through electromagnetic induction, can give rise to electric fields. But that's not necessarily radiation. Okay, we'll explain that a little bit more carefully in a moment. But also importantly, and electromagnetic radiation. Okay. Now, I only kept this first order term because I'm keeping terms to the same order in our small parameters. So this is of 0th order in the small parameter. This is a first order in the small parameter because this depends on the size of the distribution over R compared to this. So it's got like a d over R. And this has a CT, which is also a small parameter because the time derivative is like that. And that compared to D over CT is smaller than what we have over here. D over CT is another small parameter. D is the extent of the source. T is the time scale over which this changes. So this is all kept to a consistent order in our small parameters. All right, now we need the vector potential. And we do the same kind of extension. Let me get my notes on this. Okay. Before I do that, let me just remind you. Remember when we were doing multipole expansions in magnetostatics? It was kind of a nasty thing. This first term here vanished. We related that to the magnetic monopole. And we argued, we showed that that term was 0. We had this aside here, which says this is the integral x prime. Now the integral over x prime of j x prime was the same thing as the minus the integral of x prime times the divergence of j. Okay, using some tensor algebra. We showed that some months ago. Now, when we're talking about this in the context of magnetostatics, magnetostatics is defined by the fact that divergence of j is 0. But now we're not talking about magnetic statics no more. We're talking about dynamics. And so, what is the divergence of j? Conservation of charge tells us that is equal to negative rho dot. Excellent. So the minus signs cancel, and this becomes the derivative with respect to t of the integral x prime rho of x prime at the t naught, which is equal to the dipole moment at t naught, electric dipole moment. So this contribution here is equal to the derivative of the electric dipole. Remember, when you have moving charges, moving dipoles, you can have current. We had so-called polarization current when we're looking at the macroscopic maximum. So this is the lowest non-vanishing term to the same order that we kept here. So to the same order that we kept, that we retained in phi, the vector potential is approximately equal to P dot over C R. Okay. All right. Now I'll get my notes to remind myself of some things. Nope, that's not the right ones. Okay, so far so good. All right, so up to terms in electric dipoles, these is what we got. The potential. All right, so now what we're interested in ultimately is not the potentials, but the fields. So, how do we find the fields from the potentials? Remember, we have to pay close attention because the electric field depends both on the vector potential as well as the scalar potential. So my electric field is equal to minus the gradient of the scalar potential minus 1 over c dA dt. All right. So we got to plug that in. This is equal to, let's take this derivative because that one's easy. That's equal to minus 1 over c squared with rho double dot evaluated at t naught for r And then we have to do minus the gradient of the scalar. As we'll see in a moment, this is the term that has to do with electromagnetic radiation, really. That second derivative in time of the dipole moment is related to the acceleration of the charges. And you remember that accelerating charges radiate. So it's the second time derivative that matters. This is going to be related to a piece that makes this a transverse function, as it must be in free space, far away from the charges, as well as the parts that are not related to radiation, which are the near field contributions. Okay, now there's a whole bunch of algebra that's boring as all hell, so I'll just skip it and give you the answer. Okay, so just as a note. When taking the gradient, if we look at, for example, the gradient of r hat dot p evaluated at p minus r over c, r squared. Right, that's one of our terms over here, this guy. We have to make sure that we take the gradient with respect to r, but also this thing depends on the argument. Right? So when you take that, you have to use the chain rule to make sure you take the gradient on this as well. That's where things get messy and in the way. Yeah?
Do you have to worry about the unit vector because it's...
Well, we've got to write that out. Remember, how would I do this? I would take this as the gradient of x dotted into p over r cubed. Write this as x of I, p sub I evaluated at the retarded time. Right? And then I would, this is the gradient. Now I would look at the jth component of that. And I would I have to use all that tensor algebra stuff that we did earlier in the semester. It's no fun to watch that. Maybe it's not fun to watch any of this, but at least pick and choose. It might do a little bit more. Okay, so what do we get when we do that? So the electric field comes out to be the following. We have the Coulomb field, that is to say 1 over r squared times the total charge, right? That's just the Coulomb field. We have the electric field of a dipole, which is evaluated. So the field of an electric dipole in statics, you remember, falls off like 1 over r cubed. And this is the anisotropic dipole field, the one that looks like that. That's this. Then we got other stuff. Plus 3 r hat dotted into p dot at the retarded time from the origin minus the first derivative c r squared. That came from this kind of thing. Taking the derivative, the chain rule will give us that first derivative. And then finally, minus 1 over c squared p double dot p dot minus r hat divided by 1 over r. Okay, so this first term comes from the vector potential. That's what we had over here. And the second term comes from the scalar potential, which subtracts off a piece that's along r hat. Okay, so how do we interpret these different terms in the field? Oh, before I do that, I guess I should write down what the magnetic field is. And what you get when you take that curl, and the details are shown here in the notes. So, how do we interpret these fields, this electric field and this magnetic field, associated with this approximation up to the dipole terms? Let's consider the case. This is easy to interpret. This is just a Coulomb field that we would see. Let's look at the case where we have a neutral charge, a neutral distribution of charge. So let's just consider the case, although it's not so important. That the total charge is 0. So, what do we have here? Well, we have a term that's falling off like 1 over r cubed. That we said was kind of like this electric dipole distribution at the instance of time, depending on what the strength of the dipole is. And this is what we had in statics. So this is the quasi-static E field of an electric dipole. This term we call, this is complicated, we'll discuss it in a moment, we call the induction field. And this term is what we call, the term that falls off like 1 over r, we call radiation. Similarly, for this is the induction field, and this is radiation. Why do we call it as such? Well, the important thing is, how does the field fall off as a function of the distance from the origin? What characterizes the radiation, electromagnetic radiation, from a localized distribution is that it falls off like 1 over r and no faster. Why is that electromagnetic radiation? Why would we consider that to be electromagnetic radiation, whereas the things that fall off faster than 1 over r in the field, this is not the potential, this is the field, is not considered radiation? Well, what that has to do with is the question of whether or not the energy can be radiated away to infinity. So here's the source, it's doing its thing, and it's radiating or creating a field. And we want to know, what is the flux of energy through a sphere as the radius of that sphere goes to infinity? Well, that flux of energy is given by the Pointing vector integrated through the surface of the sphere. Okay? And the Pointing vector, let's look at the time average, not that that matters much, but it's just easier to write it down this way. It's proportional to the magnitude of E squared, or E times B, if we like. But so let's write it as E times B. Let's emphasize some facts here. So let's go back and forget about the time average. This is proportional to E cross B. The area here scales is on the unit of area on the sphere is proportional to r squared times the unit of solid angle. So if E times B falls off any faster than r squared, then as the radius goes to infinity, the product of the intensity times the area will fall off with distance. And as the radius goes to infinity, there'll be nothing left. There'll be no flux. In order to have the flux go off to infinity, in other words, the energy be radiated away, then this must be, so in order for S dot n hat dA to be finite as r goes to infinity, the magnitude of E cross B must be proportional to 1 over r squared. So that the product of E cross B and this is a constant. So that whatever energy is radiated through that surface, no matter where the surface is. That's what we call radiation. Radiation is the fields detaching themselves from the charges, having a life of their own, being free to fly, and leaving the mothership. Okay? So, these are the radiation. These are the terms that correspond to radiation. In the context of the electric dipole, what we see is that there is, if we're close enough in, there is a field that looks, so if I were to sketch, suppose I have a dipole that's oscillating. Okay, what would the field look like? Well, nearby, when r is small, this term dominates, right? So we have this kind of electric dipole. If we're far enough away from the source, that this thing falls off like 1 over r cubed. It's tiny. We would see radiation, which would mean we would see wave fronts that are so here's my electric field, up and it's down, it's up and it's down. These electric field lines out here, they have zero divergence, they close on themselves, they correspond to the radiating fields inside the quasi static field. In between, well, it's kind of a transition, it's kind of a giant mess. But what we know is that if we have some oscillating fields, they create currents. If those currents are changing in time, magnetic fields change in time. If the magnetic fields change in time, then according to Faraday's law, you get electric fields. That's the induction terms. Okay? But you remember from our problem set that that energy never radiates away. You can bring it back to the sources. Remember this, we spun up the cylinder, we made electrical energy, but then we can de-spin the cylinder and all the energy comes back. That's not true for radiation. For radiation, there's a dissipation of sorts. Energy is lost, it flies away, and unless there's a mirror out here, it ain't gonna come back. All right, so let's take a closer look at these terms again to understand these different, what we call radiation zones. What we found up to electric dipole contribution, and we just restricted ourselves to the case where we're just ignoring the monopole, which doesn't do anything. Notice that because the monopole is constant, it doesn't contribute to radiation. In fact, even if the monopole was changing in any way, it doesn't appear, there's no derivative of the monopole anywhere. There's only derivatives of the dipole. So monopoles don't contribute to radiation. The first non-vanishing contribution is a changing dipole, electric dipole, not changing monopole. So that's why I'm just ignoring the monopole contribution, because it doesn't do anything relative to radiation. So what we found is that the electric field we had three contributions. We have something that goes like the strength of the dipole over r cubed, something that goes like the derivative of the dipole over c r squared. This is what we call the static, the induction, or quasi-static, the induction, and the radiation. Why do I say this term dominates when I'm close to the charge, and this dominates when I'm far, and then there's this intermediate zone? Well, what we said is here, let's assume we had a characteristic time to change of the charge distribution, or change of the dipole moment. C, which each, for example, could be the period of oscillation, if we have an oscillating charge. Then we can look at the scaling here. This is so the question is, how big is R compared to CT? There are three length scales in the problem. There's the size of the source, there's where I am, and the distance light travels in the time t. The relationship between those three different distances tells us something about the relative strengths of these different terms. If t is like 1 over omega, then CT, right, is like C over omega, which is like lambda, if we were thinking about this as an oscillating charge distribution. So this is like lambda So here I factored out the same term Q over R cubed. The question is, how big is R compared to lambda? When R is small compared to lambda, then that's what we call the near field. When R is big compared to lambda, that's what we call the far field. And this we call the induction zone, or the intermediate zone. So that's why this picture looks like it does. When we're looking at our source at a distance that's small compared to the wavelength associated with the radiation at the characteristic frequencies, it looks quasi-static. If we're looking at the source way far away, where the distance is big compared to that wavelength, then we see the radiation. So if I have, suppose I have a coil of wire, which is oscillating at a megahertz. Well, if I'm looking at it near the coils, it looks like a Helmholtz coil with a magnetic field that's just changing back and forth. But if I look at it way far away, then it looks like an antenna, which is radiating, well, in that case, magnetic dipole radiation, but, you know, the same idea. So the nature of the field that we see depends upon where we are. When we're close enough to the source, it looks quasi-static. When we're very far from the source, we see the radiation, if there is a radiation term to be had, which means if there is a second time derivative, there's acceleration. So you remember when we were talking about quasi-statics, we said if the time it took for light to travel across my inductor was instantaneous, essentially, compared to the time scale over which the currents changed, we didn't need to think about radiation. That is where that approximation came from. All right? Okay, physics we need to understand. All right, so let's now, in the last bit of the last 10 minutes, let's talk about what does the radiation field look like and what are some of its characteristics. So, what we call dipole radiation what we have is that the electric field, that position in time, is that term that's circled over there. It's minus P double dot evaluated at T naught minus R hat dotted times R hat dotted into P at T naught over C squared R. Okay, the magnetic field, we said, equal to minus r hat crossed into p double dot. Not r squared r. So what can we say? Does this have the characteristics that we expect from electromagnetic radiation? And what kind of, is this a plane wave? Is it a spherical wave? What the heck is this? What kind of radiation are we talking about? Let's consider the case where we have a dipole which is moving linearly in some direction. So this is P as a function of T. Okay, it's going, it has some charges moving along a line. Gives us some electric dipole like that. Let's say at some instance of time, its time derivative is along this direction. Now, I'm at some distance from this dipole. The electric field I see, so this, let's say, is P double dot, is in that direction. Here is r hat. What direction is the electric field that I see from the electromagnetic radiation at that point? In what direction is it? Well, what I have to do is I have to subtract off the component of, this should be double dot, pardon me, excuse me. I have to subtract off the part of P double dot that's along r hat. So there is a part of this vector which is parallel, and there's a part of this vector which is perpendicular to r hat. And I subtract off the parallel component. And the electric field associated with the radiation is the transverse component of P double dot. That's what's here. This is the component of P which is perpendicular to the direction in which the wave is propagating. That's what we expect. We expect transverse waves. What about B? Well, B is just R crossed into E, which is kind of what we expect. We know if we have a wave propagating in this direction, then the direction of the magnetic field is given by the cross product of the direction of propagation with the electric field. So the magnetic field here, this is E, and this is B. So these are transverse waves. Perpendicular to direction of propagation radially outward. They're spherical waves. And we could see that spherical wave nature more explicitly when we take the particular condition that the time-dependent dipole is oscillating harmonically. So let's consider harmonic oscillation. P, as a function of time, let's say is the real part of some vector. For the moment, I'll just make it a real vector. Okay? That means that E, the radiation, will end up radiating for electric dipole with that same frequency. Well, it's actually as a function of position and time. So it's going to have some complex amplitude as a function of position. Let's put that in. Let's plug this in to this formula for complex frequency. So my radiated field, which ultimately I'll take the real part of, is equal to, each dot becomes a minus I omega. So I get omega squared over c squared. I get this evaluated at t minus r over c. That's at the retarded time, at from the origin. That's from this thing. And then I have P naught perp over r, where P naught perp is equal to P naught minus the component that's along r. What is this? It's a spherical wave. This is equal to k squared times e to the I k r minus omega t over r times P naught perp. So the electric field radiated by this oscillating dipole is a spherical wave. Note, where did this kr minus omega t came? It came from the retarded time. It's just saying that the field that I see, the oscillation that I see at my time, depended upon what the oscillation was doing at an earlier time, depending on how far it traveled. That means that they have to phase shift the oscillation I see by the phase accumulated by the amount that it propagated. That's all that means. That's all what Kr means. It's a phase shift relative to the source oscillation. Now, there's one last piece that I want to, before we quit, is what about this P perp business? What this says is that the strength of the electric field is not isotropic, even though the wavefronts are spherical. The strength of the wave is not the same at every position along here because of P perp. So if this is P naught, this is the direction of oscillation, and I'm looking at it over here, and this is the angle theta, then P perp is equal to the magnitude of P naught times the sine of theta. So that is to say that if I were to look at the strength of the radiation, if I'm looking at it over here as my eyeball, and the oscillation is here, there's no radiation along there because there's no way for it to be transverse. Sine of theta is 0. If I'm looking at it over here, I see only transverse oscillations. I see strong fields. And as a function of theta, I see the strength of the field as a function of theta falls off. This is what's known as a dipole radiation pattern, which we will discuss more next time. All right. Okay, these notes will be posted. Lots of good stuff to read. With the source, then the general solution is a weighting of the strength of the source by an amount that falls off like 1 over the distance. But what we see, the wave amplitude we see at our time t, at our position x, depends upon what the source was doing at the retarded time. The retarded time is the time, the current time, minus the time it takes for a light signal to travel from x prime to x. So what I see currently is what the source was doing in the past. Of course, you know, astronomers know this very well. So we can depict that on a space-time diagram where this axis is representing one coordinate of space, and this is time. And thinking about this is my position at the present, time t, and the signal that I see at my position at the present depends upon what the source was doing on my backward light cone. Meaning to say, what we do is we formulate things in terms of the potentials. We solve for the potentials given a certain source, and then find the fields from the potentials. So these are the equations, Maxwell's equations without the sources. They are the ones that determine the relationships between the fields and the potentials. And these equations we see have gauge invariance. That is to say, we make these transformations on the scalar and vector potential, then the fields are left unchanged. So there is a freedom we have in choosing these functions that give the same physics. And we can in principle make a gauge transformation in this way. So when we take these potentials and we plug them into the source equations, the Ampere's law and the Gauss's law, then we find these equations of motion for the potentials. Okay? And they can be written different ways depending on our choice of gauge. So two standard choices that are made in thinking about electrodynamics are the solutions. Both are solutions. And they're used in different contexts. In particular, in scattering theory, when we think about in and out waves with asymptotic boundary conditions, we often use, in the time-dependent formulation of scattering theory, one uses both the advanced and retarded time solution. But in the current context where we're talking about a source that is radiating, we're looking for the radiation that emanates from that, then we think about the causal solutions, and those are the retarded time solutions. Those are the causal solutions.
Is there any particular reason for the naming scheme?
Retardation, I think that's, you know, that is one semantic notion of if something is retarded in time, it's backwards in time. It's one semantic meaning of the word. It means it's in my future. That's where that comes from. There's no political context in this. All right. So we then see that if we convolve the Green's function, last time we started this important discussion of understanding electromagnetic radiation, and we have some prescribed sources that are moving in space and radiating electromagnetic waves. And to do that, we began by looking at the wave equation for a scalar wave that is being driven by some source term. And to solve that equation, the particular solution is found in a general form by convolving the source in space and time with the Green's function associated with the wave equation. So we looked for solutions of this equation, which we found, and we found two kinds of solutions, so-called retarded solutions and advanced solutions, which correspond to either spherical wavefronts that are emanating from X prime, or converging onto x prime. Okay? The wavefronts that are emanating from the point are the retarded time solutions. The ones that go backwards in time and converge on the point are the advanced time. These are all the space-time points in the past, in my past, correspond to this current time, that correspond to a light signal that can reach that point. And so the total signal that I will see will be a weighting of the sources over all the world lines that cross my backward light cone, added up appropriately with the 1 over distance scaling that's related to the spherical wave. All right? It's a nice picture. So now we're looking at this in the particular context of electromagnetism. This is a general formulation of waves, whether this was the speed of light or the speed of sound. The same mathematics holds, and the same physical description would then hold in that case as well. Things get a little bit more complicated for electromagnetic waves because they're vector waves. Okay? And so anyway, to do this, so we're looking now for general solutions to Maxwell's equations. And to do that, what we